Okay, so let's get started. So hello everyone, welcome to SNAPP seminar series. My name is Weina Wang. I'm an assistant professor at CMU, and I'm going to be the host today. First, let me briefly remind you of some logistics details. Please mute yourself when you're not asking a question. But you are encouraged to turn your videos on so Qiaomin can see several faces. And the talk is being recorded. Also, it's being live streamed on YouTube. If you don't want to appear in the recording or on YouTube, you can turn off your video and mute yourself. Or you can just head over to YouTube and watch the talk there. If you have a questions. If it's a quick clarification question, you can type it in the chat box. I'll relate those kind of questions to Qiaomin. If the questions are longer than that, you can either wait until the question breaks Qiaomin is going to have, or you can wait until the end of the talk where we're going to have a Q&A session. Okay, so today we are really excited to have Qiaomin join us. Qiaomin is a visiting assistant professor in the School of Operations Research and Information Engineering at Cornell. Prior to that, she was a postdoc with Liz at MIT and was a research fellow at the Simons Institute during fall 2016. Qiaomin received her PhD degree in electrical and computer engineering from University of Illinois, Urbana-Champaign, and her BE degree in electronic engineering from Tsinghua University. So her research interests lie in the fields of applied probability, reinforcement learning, and the stochastic networks. Qiaomin is the recipient of Google System Research Award 2020, UIUC CSL PhD Thesis Award 2017, and the Best Paper Award from IFIP Performance Conference 2011. So today, Qiaomin will be talking about the power of Monte Carlo methods. So the floor is yours, Qiaomin. Welcome.
Thank you, Weina. Could you hear me clearly?
Yes.
Good. Thank you for the nice introduction. Big thanks for the organizers for having me here. It's my great pleasure to speak at this exciting seminar series. Today, I will talk about my research work on understanding and applying the Monte Carlo method. This talk is based on several papers with my excellent collaborators. Please feel free to stop me if you have any questions during the talk. We know reinforcement learning is about the study of sequential decision making, where an agent interacts with environment to gain long-term reward. And in the past few years, it has achieved the remarkable empirical success in many applications, including games and robotics. And it also shows the promising performance in other areas, such as healthcare, education, and chemistry, etc. The standard framework for reinforcement learning is the Markov decision processes. In an MDP, an agent or the decision maker interacts with the environment as follows. At each time step, the agents will observe the state of the environment and take some action and receives the reward. And then the environment transitions to a new state and the interaction repeats and continues. A stochastic policy for the agents map each state to a distribution of actions. So basically it specifies the probability of taking a particular action given the current state. Now, the goal of the agents here is to find a policy that maximizes the expected total discounted reward. And the gamma here is the discounted factor between 0 and 1. When the model is unknown, if we don't know the transition kernel or the reward, then it becomes the reinforcement learning problem. Now, the agents want to learn a good policy through the interaction data with the environment. It can be real experience data or data from simulation. We know in an MTP, the value functions can be defined in two different ways. So now let's fix a policy type and a state action pair as A. And the original definition of the state action value, or the so-called Q value, is the total expected discounted reward starting from this particular state and this particular action at the first step, and then the follow policy type for subsequent actions. So by this definition, then we can simulate one or maybe multiple trajectories under the policy type, and then use this to mean empirical return as an estimate for the Q value. So this is the one definition. We also know that the Q function satisfies the so-called Bellman fixed points equation. Now, suppose that we have an access to an estimate, the Q function, Q old hat here. And now, given a single step transition data starting from state action pair as A, then we can update our estimate for the SQ value as the sum of the immediate reward and the discounted old estimates of the next state action pair. So here we bootstrapped for an existing estimate O hat here, which serve as an estimate of actually the remaining terms in the summation above here. And these actually the ideas for value iteration, the Q learning algorithms. These two ideas are, to me, I think they are the basis of reinforcement learning. And many methods used a combination of these two ideas. In this talk, I will focus on Monte-Carlo idea. That is the methods that have a significant simulation component. And so it's closer to the first extreme here. And one example would be the methods that use the multi-steps look ahead, rather than just single steps look ahead. Many well-known reinforcement learning algorithms are primarily based on Bellman's equation, including the value iteration, TD learning, Q learning, fitted value iteration, etc. They're popular and extensively studied. In today's talk, I will focus on understanding Monte Carlo approach, which is also very powerful. MC methods take advantages of simulators, which are available for many applications. And some domain might have abundance of real-world data that can be utilized to build an approximate simulation model. And also, as we have seen in the previous slide, we can just focus on the value or the policy locally at a single state we are particularly interested in without solving the entire MDP. So the complexity here actually does not scale to the size of the state space. And this is really nice. And as a result, we can do the decision time planning, meaning planning only for the states we just encountered in real time. Another advantage is MC method is more robust when the environment is not truly Markovian. In contrast, Bellman equation relies on non-Markovian assumption. Applications that the benefits from MC methods, including games like Go and video games. Another motivating application myself particularly interested in is in queuing network control. Usually here it's easy to simulate either from an artificial simulator or synthetic simulator built from real world data. And the state space here typically are unbounded. So it's impossible to learn a policy for all states in the state space. And the local property of MC method makes it well suited for learning when a new state is encountered. So we can do the decision templating. And also, we can still use the MP method even when the arrivals and the surveys are not Markovian. Of course, I should mention that there are other applications like healthcare for which the MC method are thus appropriate, since a simulator is not available and data is actually very expensive and difficult to obtain. With this background in mind, I will talk about two of my work related to Monte Carlo methods. First, I will focus on Monte-Carlo Tree Search, one of the most popular and empirically successful MC methods. I will talk about its non-asymptotic guarantee and the several extensions. Then for the second part, I will focus on data-driven queuing network control. I will talk about how to achieve stability by using MC method and how to achieve optimality given a stable policy. Okay, that's the start with MCTS. Monte Carlo Tree Search is a search framework for finding the optimal decisions. And it's first introduced in 2006 by Chang and Tao. There are many variants of MCTS. In this talk, I will focus on the most popular one in the family called Upper Confidence Bound for Tree, or UCT. And it has been used in many applications and achieved remarkable empirical success, including the computer program that defeats human champion in the game of Go. However, despite its popularity, its rigorous performance guarantee actually is not so clear. And this is exactly what I'm going to talk about here today. Here, I assume that we have access to a simulator, so we can sample trajectories. Now, the goal here is to find a good action for the current state ST. This is the stage where we are now, and we care most about what should I do for the current state. Then it means we don't need to really solve the entire MDP for every single stage. We just need to focus on the sub-MDP starting from the current state ST. Okay, so this is the goal here. Now, at a high level, MCTS combines the ideas of simulation, multi-step look ahead, and smart sampling. To be more specific, here we will imagine what might happen starting from now in the short-term feature by simulating multiple trajectories here, starting from the current state ST. And moreover, we learn from this imaginary experience, so we can allocate further future simulations to the most promising trajectories like here. In my opinion, I think the most important ingredients for MCTS is the smart sampling. This is actually what makes MCTS the more powerful than naive the Monte Carlo method, but also make the analysis challenging, as we will see later. Now, let me illustrate the details of MCTS. For simplicity, assumes that there are only two actions, A1 and A2, and the decision is deterministic. We can easily generalize to the setting with stochastic transition. The tree here represents all the possible trajectories from of the MDP, starting from the current state ST up to H steps. And this is an example with 3 or with 5 steps. Each node here represents the state. And the loose node is the constant state ST, and each edge corresponding to an action. From the constant state ST, action A1 leads to state S1, and action A2 leads to state X2, and so on for other states and continue. I want to point out here, this is an imaginary tree, so that's why I use dash line here. In implementation, MCTS actually starts with an empty tree only with the loose node for the constant state, and then gradually build this tree from state actions encountered during the simulations from the trajectory. Here we will simulate multiple trajectory up to edge steps, and always the starting from the constant state. For instance, the first simulation is this trajectory, which is a sequence of state action, reward, the next state, the next action, next reward, etc. And here, the superscript K indicates this is the case trajectory. Now, when we reach a leaf node here, suppose that we have an access to a value estimate, function estimates, V hat, then we can use it. If we don't, then we can simply just assign the value 0 for the leaf node to as an approximate estimation for the future reward starting from this particular stage. And now for each state action pair on the trajectory, we will keep an estimate Q value by using the returns from the trajectory starting from this particular state action pair, like what we have seen the previous day for the Monte Carlo simulation. Okay, so this is the one trajectory. We run the simulation and reach a leaf node and do the updates for state action pair. And say the second trajectory is here. And similarly, we update the Q value for state action pair encountered on the trajectory. Now, for the state action pair here, we'll update its Q value as the mean of the returns from these two different trajectories. Similarly, we might have our trajectory and we do an update. Okay. Now, when we finish its n simulations or n trajectories, we output the estimated Q value for the loose node for every single action. And with these estimated Q values, we can actually obtain the policy for the constant state or the loose state ST. It can be either greedy with respect to the constant Q function estimate, or you can use softmax with a temperature tau here. Okay, so this is the basic idea of MCTS. But wait, one thing I haven't specified yet is what action should we choose at every stage during a simulation. So the policy used to choose the action is called the tree policy. It's guide how we do the simulation. Of course, the most simplest one will be choosing actions uniformly randomly. And these will corresponding to so-called sparse sampling studied earlier by Constantine, almost 20 years ago. Okay, MCTS actually used an adaptive policy. Here, we'll borrow ideas from bandit literature and treat the decision-making at each stage on the tree as the multi-unbounded problem. Now, to choose an action, we can use a classical bandit algorithm called upper confidence bound. And in contrast, for each stage action pair on the tree, we keep an estimate Q value, which is the empirical mean of the prior trajectories returns. And according to UCB, we will choose an action that's the maximize the sum of the empirical value and a bonus term. And typically, the bonus term here encourage exploration for actions that have not been visited often so far. And we know in multi-unbounded, the standard choice for this bonus term is logarithmic in T. Here, T is the total number of visits for the states as so far. And this choice actually comes from the Hofding concentration inequality for IID reward sequence. Okay, so this is just the classical bandit algorithm. However, it's turned out that for MCTS, with a tree structure here, we actually need to use a bonus term that is polynomially in T. This is actually very crucial. We will come back to these points later. Okay. If we use the polynomial bonus term here, then we can establish the following guarantee for MCTS. Suppose at each simulation, we use an old estimate, V hat old, for the leaf node, which is the epsilon accurate. Then if we run the n simulation or trajectories, each up to edge steps, and output the estimate Q value for the loose node ST. Then we can obtain an upper bound for the errors for the loose nodes the Q value estimates. And the error consists of two parts. The first part is due to the errors at the leaf node. And the second part comes from the finite simulations. So if we let the number of simulation and to be sufficiently large enough, then the first term will dominate. And because that gamma is the discounted factor between 0 and 1. So we can ensure that this term is always smaller than the accuracy epsilon for the leaf node from the old estimates. So we can think MCTS improves the estimate for the loose node over the old estimates. And given the estimate Q value, it's always easiest to obtain the estimated V value for the constant state ST. Okay, so MCTS can provide improvements to estimates. I want to point out here is the theorem is actually still useful, even if we don't have an estimate for the leaf node. We can simply plug in 0 value for the V hat old. And now the epsilon satisfy a trivial upper bound when the reward is bounded by some constant dynamics here. And this can still ensure the improvements if we have sufficient number of simulations for MCTS.
Qiaomin, I have a question.
Yeah. Yes.
So what do you mean by N simulation? So is this here in your last display in your theme? Is that ST is you start from that particular state or a bunch of states on some sample? I mean, what's the meaning of the last result here that is display? ST.
Okay. Mm-hmm. So if I go back to the let me show you the figure here. This will be easier. So this is the state ST, which is the loose node, the state we care about most at this point. And we run n simulation, each simulation corresponding to one trajectory up to edge steps here. So the red one is the one simulation, the green one is the second simulation, and the blue one is the third simulation.
So you'd say that for the first stage, which for A1, A2, is that going to be exhaustive? That's also using smart sampling, or just some A2 will be select more than A1 or something? Or the future nodes, I know I understand, but for the root node, is that also smart sampling?
Yes, for the loose node, we can also use smart sampling. But okay, so not really. So we don't use the smart sampling if we want to estimate the Q value for every single Q action. So for all remaining action, we can use smart sampling. And for the loose node, we can kind of uniformly sample each of these actions in order to get an accurate estimate of the Q value for every single action. You are right. Thank you for pointing this out.
Okay, so let's go back to your theorem now.
Yeah.
The theorem is stating just guarantee for that state root node, that root node.
Yes.
Is that, but of course you want to get something for all the, right? You want to algorithm something that guarantee that all the nodes goes through not just one, that one, right? There's lots of states.
Exactly.
Right. So how do you relate to that? I mean, this something this your results will be help to get some results for the. Can you say something? Yeah. Okay.
That's an excellent question. Actually, that's the basis of our proof idea. We kind of, I will come back to this later. So basically, we can also obtain the guarantee for every state action pair we encounter during simulation.
Okay, good.
Yeah,
thank
with
you.
similar results, but of course, the different parameter or different guarantee. Okay. Yeah. Any other questions that before I continue to the proof idea?
I have a couple of questions. One is kind of follow up to Jim's question. So you said how MCTS is a local approach. Like if I'm interested in a particular state and I want to find the optimal action for that state, I should do this. Why is that an interesting question? Because in an MDP, usually you want to find the optimal actions for all states, right?
Yeah, that's an excellent question. So in terms of the local, I think in terms of the local property, so here, what I mean here, the local means you can just focus on your current states you are interested in here. And in terms of why we're interested here, in some application, so if the state space is huge or uncountable, then it's impossible to solve the entire MDP for every single state, right? You might want to focus on states that are interesting, meaning states you might visit more often and you can learn good estimates for these states. But for other states, we can occasionally visit these states. But since you don't have any prior knowledge or you don't learn much, so then in such states, we can use this Monte-Carlo Tree Search to provide a good action.
Okay.
Yeah. Qiaomin, I'm interpreting it slightly differently, actually. So you just start from a particular state and then you do this. But then, I mean, if you think about AlphaGo or other things, you do this at a few states, but then you try to generalize using a neural network. I mean, you won't use, I mean, right now you're treating it as though it's tabular, but I think it's because you're just looking at one particular node. But then you would use this estimate to update the parameters of a neural network, which sort of allows you to generalize it across multiple nodes. Isn't that the way they're using it in AlphaGo? So you're just looking at one portion of the AlphaGo algorithm, if I understand it correctly. Is that right?
Yes.
So what I'm saying, you don't need to think about this as a important node or an unimportant node. I mean, you can think of it as any node, and then basically now you try to generalize it by using this estimate to update the parameters of a neural network, which would try to generalize it across all nodes. Isn't that the way they do it?
Yes, excellent point. Okay. Yeah, actually later we'll come back to the extension, how we can combine the MCTS with supervised learning to improve to provide estimates that actually can be over all the state space.
Okay. Yes, this is something just as a Jim. Sorry to jump in. I think right. I think put this result right itself. It's very difficult to understand why. Right. This clearly is an important part of that. But I think the bigger issue here, right, something that is you eventually want to have good planning. The MDP, it's overall it's a good algorithm, right? This is just something, right? How this can be tied up with the bigger picture, and I think Srikan earlier said that something absolutely that is the key, right? Maybe I'm not sure that's the unique way to connect back to the good planning or finding the optimal policy for the original MDP, but certainly that's one possible path to connect the bigger picture. Okay, thank you.
Excellent point. Okay.
There's One more question in the chat. Is it similar to model predictive control?
Kind of like for MPC, usually you have the model. So you do the computation and then do the planning. And here we kind of replace the exact model by the simulation. But the spirit stays similar, yeah. Okay, let me continue with the proof idea here. The key challenges of proving the previous theorem are the dependency and the non-stationarity. Both arise due to the tree structure of MCTS. In particular, MCTS is the hierarchy of MABs, meaning each arm itself is the MAB. For example, consider the MAB as a loose node. Now, the left arm itself is the MAB with two arms here. And the returns to this arm depends on which arm is selected in a lower level. So it creates a lot of dependency between these random returns. Moreover, we know the subarm is typically selected adaptively as the bonus term keeps changing over time. So the return sequence for the upper level here is actually non-stationary. And with this dependency and the non-stationarity, the return sequence are not IID and no longer satisfy the classical Hopding or exponential concentration. So this is why the original UCT algorithm with a log bonus term is not guaranteed to work in general. And the original UTC paper claimed the asymptotic convergence, but actually the proof is incomplete. The key idea of our proof is to use the induction with respect to the tree depth. In particular, the induction hypothesis as follows. Now, for each arm here, the empirical average of the return actually concentrates around its limiting expectation. And the tail probability here is the polynomial rather than exponential. And we can ensure this property if we use the polynomial bonus term. So this will answer Jim's question. We can actually establish similar performance guarantee for all state action pair we encountered in simulation. And an interesting fact here is AlphaGo 0 also used a similar polynomial bonus term. Okay, I will discuss some extensions of the results for MCTS. So far, we have seen that for each query state S, MCTS can output an improved or high quality estimate. And we can do this for finite many states, say n states. And now the question here is, can we generalize these improvements to other unseen states? So these actually relate to Siva's questions about why we only cared about a single state. It's not really the case. We can do this for a finite number of states. Now we can achieve this generalization by formulating as the regression problem. We want to predict the value or maybe the Q value for a query state. And we are given M training data points here. S is the feature and V has is the label. Now you can use your favorite supervised learning algorithm. As Srikant mentioned, AlphaGo 0 use deep neural network for supervised learning. And you can also use non-parametric regression, such as nearest neighbor. And moreover, we can do this iteratively. So the MCTS will generate the new high quality training data, and supervised learning will generate these estimates to the entire state space. And we can in turn use these outputs of supervised learning as the leaf node estimate for MCTS, and which generates a new improved training data and so on. So together, MCTS and the supervised learning serve as the strong policy improvements operator in the high level sense. Okay, so we can also generalize MCTS and our analysis to two-player zero-sum game, like Go or chess. Now, in this case, the second player tries to minimize the value, while the first player tries to maximize. And the goal here is to learn the Nash equilibrium. And we have similar results for MCTS and also combining with supervised learning in this setting. And I want to mention as, so MCTS with supervised learning for game is actually a basic or simplified versions of AlphaGo 0. And in this sense, we provide a sound for more theoretical understanding for AlphaGo 0. Okay, one more extension here. So the previous results I just showed assumes the finite action space. Recently, we generalized MCTS to continuous action setting. Now, each node on the tree is a continuous unbounded. And we combined MCTS with adaptive discretization for the action space by using the idea of hierarchical optimization. And again, using polynomial confidence boundary is crucial here, and we can obtain similar convergence guarantee. We also evaluate our approach on several benchmarks from OpenAI Gym. Our algorithm, the last one here, either match or improves the other existing tree search methods. And in particular, for the challenging lunar lander problem, we achieved much better performance. Of course, from the previous, the news earlier, they don't really use the reinforcement learning. Okay, so this is just a toy example. Okay, before I continue to the second part, I will pause here in case there are any questions.
Okay, I have a question. So you said you have theoretical results for MCTS plus supervised learning, right?
Yeah.
So can you tell me a little bit about like what these results look like? Like, for example, what are the kind of function approximations you use for supervised learning, and where do you converge, things like that? Yeah,
so excellent question. We consider a continuous state space and used non-parametric, the particular nearest neighbor supervised learning regression. And under some smoothness condition on the function or the MDP itself, then we can iteratively improve the value function for all states in the state space. And the complexity will actually depend on have an exponential dependence on dimension B. But without the further assumption on the structure of the system, this is actually the fundamental lower bound. Yeah.
Thanks.
Okay. Let me continue.
So nearest neighbor means basically you're doing clustering. Is that what you're doing?
Yes, the nearest neighbor. Yeah.
Okay.
Okay. Now let's start with the second part. Let me start with some simple queuing network here. Here is the parallel server system. The action here is the scheduling decision for every server about which queues to serve when it becomes idle. And the dynamic of the system are induced by the arrivals and the service processes. And the goal here is to minimize the total queue length. And there can be constraints on which queues can be scheduled simultaneously. Then, for instance, you formed a matching here, leading to the so-called switch scheduling. And sometimes the buffer are at the server side. Then the action here is the dispatch decision for each arriving job about which queues to join when it arrives. There can be other more complicated queuing system. Existing research on these problems are mainly based on data-driven approach. So the typical design flow is the follows. We start with accurate model of the system, and then based on our intuition or domain knowledge to design an algorithm. And we might run simulation or experiment to test and tune the algorithm for good performance. And then we prove the performance guarantee. There is a rich literature on this line of work. Actually, many audience here have important contributions to this line, and it has significantly deepened our understanding of queuing network control. It's also well recognized there are some challenges here. First, the underlying system can be complicated, so an accurate model might not be available. And secondly, even if we have an accurate model, the optimal policy can be difficult to find. And this is true even for some simple models. Here, I consider data-driven approach based on reinforcement learning. This approach takes advantage of the availability of a simulator or the data sets collected from the real systems. Reinforcement learning-based approach has the potential of tackling these challenges here. It can learn the system dynamic from data, and it can also discover new policies. Of course, using reinforcement learning also has its own challenges. A key characteristic of many queuing systems is the unbounded state space. Here, the state is the q-length vector, which can be unbounded. So traditional offline training and then deployed approach might not work here. Here, you would do training using only finite samples, and then you deploy the learn policy without further change. Say the blue region here represents all the states visited in the training phase. Now, we know in queuing system, we visit some states not observed in the training phase, say the yellow states here, which can be far away from the training region. Now, for these unobserved states, the previously trained policy might not behave well, meaning it might keep serving an empty queue while the other queue is dropped. Therefore, this decision time planning is necessary here. We want the algorithm have the ability to learn a good action when a new state is encountered in real time. Due to the unbounded state space, minimizing the queue length is actually quite challenging. Even keeping the queue length to finite is highly non-trivial. So we first consider the simpler problem of maintaining finite queue length, which means the stabilizing the system. Stability is the necessary first step towards the optimality here. We consider following notion of stability that is appropriate for reinforcement learning. More specifically, we will call a policy sequence stable if the underlying system satisfies the two conditions here. The first one is boundedness, which means that the most of the time, the system will stay in a bounded region here. And the second one is recurrence, meaning that if occasionally the system visits some states outside the bounded region, but it has the ability to recover from such undesirable states and returns to a bounded region within the finite time step. So you might notice this, the definition is quite similar to the standard definition of positive recurrence of time homogeneous Markov chain. The one key difference here is we allow the policy sequence to be non-stationary because in reinforcement learning, the policy can be updated over time. So the question we're interested here is for such an unbounded state space setting, how can we learn a stable policy purely from data? Our idea is based on Monte Carlo search method. Overall, the algorithm worked as follows. Now, at each time step, it will first query Monte Carlo oracle for the constant states and gets the distribution over actions. So the distribution serves as the policy for the constant states. Then we will take an action according to the suggested distribution, and the system transitions to the next stage. And then to repeat this process, query or gets the distribution and take action, and etc. Our hope here is the outputs from this MC oracle are close to the optimal policy in some sense. Then if the optimal policy is stable, then we might be able to claim stability of the approximate policy sequence. Moreover, we hope that for each query, the oracle can compute such an approximate policy by only using finite samples. There are a couple of choices for the MC oracle. One is sparse sampling that's used to uniform random simulation. And the other is the Monte Carlo Tree Search we have seen earlier. And recall that for MCTS, we propose the parameters. The estimate Q value for the query states can actually be close to the optimal Q value with high probability. So if we construct a softmax policy from the estimate Q value, then we can bound its distance to the optimal policy for this particular state. And in particular, the error bound here can be made arbitrarily small, as long as the error bound epsilon for the Q value is small enough, and we choose a proper temperature term. Of course, the natural question here is how small the error should be in order to achieve the stability, and what's the sample complexity per time step. To answer these questions, I will introduce the assumption here. In order to have hope for stability, the optimal policy itself must be stable, which means the optimal policy leads to a positive recurrence to Markov chain. And in queuing, this means the system load is within the capacitive region. It's also well known that positive recurrence is equivalent to the existing so-called Lyapunov function. This motivates us to assume that the Markov chain under the optimal policy satisfies the Lyapunov drift condition. More specifically, we assume that the possible change of the Lyapunov function during any possible transition is bounded. And secondary, for each state, such that the Lyapunov function is above some threshold, we'll have a negative drift minus alpha here. Indeed, such a Lyapunov function exists for many queuing systems. For a single server system, it's well known that the optimal policy is the senior rule, and a linear function satisfies this assumption as a valid Lyapunov function. And I just want to emphasize that our algorithm does not need to know the exact Lyapunov function. Under this assumption, with proper guarantee from the MC oracle, our algorithm outputs a stable policy sequence. Here, remind you that the epsilon corresponding to the error for the Q value estimates for a query state, and the tau is the softmax parameter, and the minus alpha is the negative drift of the Lyapunov function. So as long as the epsilon is small enough and the temperature is chosen appropriately, then the policy is stable. Moreover, the sample complexity per time step is finite, and it scales with the drift parameter as follows. And you might notice that the sample complexity scales super polynomially in 1 over alpha. So it means the algorithm can be highly inefficient when the alpha is small. And we know in queuing system, small drift typically corresponding to high load regime, which is often the regimes of interest. We have refined version of our algorithm that can actually improve the sample complexity from super polynomials to polynomial in 1 over alpha. And the D is the dimension of the state space. Also, while I mentioned that the algorithm does not need to know the exact Lyapunov function, but the parameter actually indeed depends on the drift parameter as we have seen from the result, which is unknown. We develop an adaptive version that can automatically discover a proper parameter, epsilon and tau. And the key idea here is to construct a statistical hypothesis testing for whether or not the Q-length is growing or whether or not the system is unstable. I'm happy to talk more details about it offline. Okay. So before I moved on to optimality, any question about the stable part?
I have a question.
Yeah.
So you mentioned how MCTS can be used when you have an access to a simulator, right? And
yes.
Then in your algorithm, like every time you use MCTS, you have to get multiple samples starting from that state. So how do you do this in a queuing system? Because you can't reset the queuing system back to a particular state.
So that's why I mean having access to a simulator. So the MCTS is actually what happened in my mind. It's imaginary. So it does not really interact with the real environment until we finish all the simulation and get an estimate action to take.
Okay, so you're assuming you have an access to a queuing network simulator?
Yes, exactly.
I see, okay.
Yeah.
So how does that make sense? Because you motivated by saying that you want to use this when you don't know the arrival rates, service rates, and so on, right? But how do you have access to a simulator which knows these rates?
So it can be an artificial simulator, or sometimes if we have access to abundance the real world data, and we can use samples from this real world data as a synthetic simulator.
Okay, okay. Got it. Thanks.
So I have a question about the stability. So
okay.
is the system stable for the particular arrival rates that you're using? I mean, so it's not like the max weight policy, which is stable for all arrival rates within the capacity region, right? So this is not a throughput optimal policy in that sense. Is that correct? Or
yes, excellent point. This is true. Our statement here, this is for a particular arrival rate. Yeah. And if you change the arrival rate, then meaning we need to set the parameter appropriately in order to achieve stability. Yeah.
Thanks.
But so I have a follow-up question, Qiaomin. So you have this like later on you have this improvement which can automatically tune the parameter. So does that like then work for any arbitrary arrival rate? Because
that's
the arrival rate will affect alpha, and that algorithm kind of finds alpha automatically.
That's an excellent point. I think we can do this, but I'm not 100% sure about the convergence guarantee or the stability guarantee.
Okay, I see.
Yeah. Okay, I think I have a couple of minutes. Let me quickly jump into the last part here. So now we know how to stabilize the system. A natural next question here is, given a stable policy, can we further learn the optimal policy? And indeed we can. The high-level idea of our approach is to divide the state space into two parts, a bounded subset and other states outside. For the outside, the red states here, we can apply a default stable policy. It can be either some stable policy we already know, or used our stable reinforcement learning policy. And the intuition here is under stable policy, the system will visit the least red states with more probability. So the associated cost for these red states can be controlled to be small. For the bounded subset, we applied a model-based reinforcement learning to learn the optimal policy. Suppose that we truncate the state space at U, then under similar assumption on diagonal function, the average Q-length under our algorithm actually approaches the optimal average Q-length, the low star here, and the gap decays exponentially in U. Let's see some simulation results here. Consider a scheduling problem with a stochastic connectivity. Here, Qi is connected to the server with probability Ci at each time step. And finding the optimal policy for this problem actually remains open for the past 20 years. For our algorithm, we'll use serve the longest connected queue as the default stable policy. And if we truncate the queue length at u equals to 5, then the average queue length under our algorithm, the red line here, converges to 3.9, which is better than the blue line here, the default stable policy. And if we increase u from 5 to 10, it's actually converged to a better value, 3.7. And we have similar results for load balancing and switch scattering. Before I end my talk here, I just want to share some of my thoughts on RL-based methods for queuing network control. Some empirical work actually show promising and exciting performance of RL methods for challenging queuing network problems. For example, for switch scheduling, we tried the MCTS combined with function approximation. And it outperforms the standard max waste matching, the red line here, and achieves comparable performance as the max waste alpha with parameter 0.1 here. And in a similar spirit, recently, Mark Grossman and Jim Dai shows that if you have an initial stable policy, then using policy optimization with neural network can actually improve the over existing algorithm for a wide range of queuing problems. Therefore, I believe reinforcement learning has the potential of finding a better policy. And of course, there are still many challenges here we need to tackle before we make it more practical and insightful. And I also believe that it's promising to combine the model-driven and the data-driven approach. To sum up, we provided two results demonstrating the power of Monte Carlo methods here. We provide a complete analysis of MCTS. We also show the potential of reinforcement learning for stochastic network control. And there are many interesting future directions here, both for MCTS and the queuing network. And as I mentioned, one direction I'm particularly interested in here is to combine the power of model-driven and the data-driven approach. That's all I want to talk about here today. Thank you so much for your attention. I'm happy to take questions.
Thank you, Qiaomin. Thank you for the great talk. Okay, so yeah, now is the Q&A session. I think there was a question in the chat. Damin, do you want to ask Qiaomin yourself?
Sure. Hello. So you mentioned that MCTS can be extended to 2 players turn-based zero-sum games. And I was wondering how the simulator play when it's the turn of the environment. How does he select actions?
Okay, that's a very good question. For game setting in simulation, it would be slightly different from the UCT I talk about. Then in this setting, it becomes so-called self-play. So you kind of played with yourself. You kind of use your counter policy or your counter belief to project what your opponents that might take in the next step and so on. And this is actually also the key idea used in AlphaGo 0 as well.
So the environment is using UCB as well, but in the reverse direction? Or?
Yes, exactly. It's instead of maximizing the sum of the empirical and the bonus, it will be the kind of a lower confidence bound.
Okay, so thank you.
So I have a question. This is Kathy. So first, a great talk. I have a question regarding the optimality guarantee. So when you, in the beginning, you mentioned the general philosophy, you want to can only focus on a subtree of learning, and then I remember you had this sequence of trees, in the Monte Carlo tree searching. And my question is about, since you're selecting of the subset of the decision or actions, it's typically sample path dependent. So often there is this problem, like, the trade-off between exploration and exploitation. So because your knowledge is only based on the sample you collected, so it could
Yes.
be, a misbelief. So how do you guarantee in the beginning the subset of the tree you select? You might have already ruled out the optimal solution because your initial kind of initial limited set of samples.
Excellent question. So then it means that you really want to get a good estimate or a good action from the MCTS for states you visited. And this can be, as I mentioned, from the theoretical results, you can see this can be guaranteed if we choose the proper parameter for the MCTS. And you need to set the depth to be deep enough, and also you run sufficient number of simulations. And in this way, you can ensure that you will get a good action for the query state.
Thank you.
Yeah.
Any other questions? Okay, if not, I'll stop the. Oh, sorry, go ahead, Varun.
So I mean, I had like a quick question about like the first result that you showed. Like, how does so you had like this order 1 over square root n term. How does the number of actions enter in that expression, or how your choice of n?
That's a great question. So the big O we have there kind of hide all the dependence on other parameter of the model. And in the worst case, the dependence can be a to the power of h. H is the depth, a is the number of action. So you can imagine this will be kind of like you expand all the possible paths from the query state. And this actually unavoidable if the problem instance is difficult. So you can imagine this kind of like a difficult instance where you try to find a needle in a haystack. There's only single reward at the leaf node. Then it means that for this situation, you will encounter the a to the power of h dependence. And and recently actually some researchers from Europe, Emery Kaufman, they have some nice results, but based on kind of like a model based algorithm, and show a nice instant dependence bound for a different MCTS algorithm. And then it kind of reflects, for some instance, MCTS can be really efficient, but for the worst case, it's kind of have a similar performance as uniform random search.
I see. So then like, so the first part was discounted, but then in the end, when you went to the queuing system, that was undiscounted. So there is no gamma here, right? So if I just use that result, your h has to be infinite. But then how do you?
That's a very good question. So I kind of like, let me come back to these results here. So for these parts, the stability guarantee, here it can be it can be average cost setting or can be the discounted setting. And now I kind of choose a little bit at a sample complexity here. And since we assume the pi star, the optimal policy is actually with respect to the discounted setting. And the country, we don't have concrete answers to what will happen if we only have the assumption on the optimal average cost policy. So in that case, the country, we need to extend the results for MCTS from the discounted settings to the average cost setting. And we believe that can be shown if we impose some condition in terms of the ergodicity of the Markov chain.
I see. Okay.
Yeah.
Makes sense. Okay, thank you.
Yeah, excellent question.
Siva teacher, are you trying to say something? We couldn't hear you.
Sorry. Yeah, I have a button on my mic. I forgot to unmute that.
Okay.
I was asking if the last truncation result that you have for queuing networks, can you interpret it as follows without any MCTS? So suppose you have a queuing network problem, and then you truncate it at some level, and then outside that level you use some stable policy, and inside the level you use some close to optimal policy, which is whose error is characterized in an appropriate manner. Then what you end up is like a close to optimal policy in this sense.
Yes, that's a very good summary of the results here.
Okay. Okay.
Yeah.
Okay.
Yeah.
Cool. I think that is pretty interesting because I think that may be of interest even beyond MCTS literature, right?
Yeah. Yeah. So here you can totally forget about MCTS, and you can use the other stable policy just for state outside the truncation.
Okay.
And the key here, we actually, so this is from the learning actually happens sequentially. We don't assume you do the sampling for every single state. So it's you learn while you playing. Yeah. Okay. It's the episodic setting in some sense.
Okay. And since the Lyapunov assumption is equivalent to stability assumption, you don't really need a Lyapunov assumption. You can just say that it's stable. Oh, but the parameter, the alpha, shows up in the theorem. So that's why you need the Lyapunov assumption?
Not really. So let me come back to the algorithm here. So basically, you want to ensure that if you use stable policy, you can ensure the guarantees to return this bounded region pretty often. And these kind of like in order to get the theoretical results, we need to impose how you can return to this bounded region.
I see. Okay.
Yeah, that's why we can kind of like upper bound the error or the cost associated with this red state.
Okay.
When you use the state policy. Yeah.
Thanks.
Okay, I think I can stop sharing here if there are no other questions.
Okay, so yeah, thank you again for the great talk, Qiaomin.
Thank you for inviting me here.
Thanks, Qiaomin. See you.
See you.
Hey, Christina, how? Sorry, I forgot what's her name again.
Esther.
How's she feeling like about the topic, Monte Carlo Tree Search?
Very excited. Doesn't want to sleep. Supposed to be her nap time now.
I can tell